ideal binary solutions. Frequently occurring topic in JEE Mains. Now, binary solutions means solution of two liquids. Okay. And ideal solution means that the intermolecular attraction of AB, the two liquids which are AB, the intermolecular attractive forces between A and B are comparable to intermolecular forces between two molecules of A as well as two molecules of B. So this is condition for an ideal solution. And since intermolecular forces are comparable, delta H of such a solution, delta H mixing, will be zero. Change in enthalpy on making the solution will be zero. Delta V mix, change of volume during mixing will also be zero. Correct? But delta S mix, entropy change on mixing, will definitely be greater than zero. Because a mixture of two things will be definitely more random than a pure component. Okay. So delta H makes zero, delta V makes zero, delta S makes zero. And the common example of ideal solutions we can take as any two consecutive members of a homologous series. It's a very common examples for ideal solutions can be a solution of benzene and toluene, ethanol, hexane, heptane. Correct? So very closely resembling ideal solution. So here, when we have ideal solutions, means we have a solution in a beaker in which there are two volatile liquids A and B, and they are making an ideal binary solution. So A and B are two volatile liquids. Volatile liquids means both can evaporate, both will evaporate. So let's say we make a solution of A and B, in which mole fraction of XA is mole fraction of A is XA and mole fraction of B is XB. Correct? Now, as we are saying, both are volatile liquids. So both A and B will evaporate. So molecules of both A and B will be present in the vapors above this solution. There will be some amount of A as well as some amount of B in vapor form above this solution. And these vapors will apply a pressure on surface of this liquid. So in this case, in this mixture, the partial pressure applied by vapors of A is given as XAPA0, where PA0 is vapor pressure of pure A. And similarly, partial pressure of B will be given as XBPB0, where PB0 is vapor pressure of pure B. So these will be partial pressures of A and B above this solution. So the total pressure of this solution, total vapor pressure of this solution, which will be partial pressure of A plus B, will be given as XAPA0 plus XBPB. We can rearrange and write it, this equation also, because if we are saying this is a binary solution, means solution has only A and B, then definitely I can say that XA plus XB will be 1. So this equation, which is P total, is XAPA0 plus XBPB0. I can rearrange and write it also as XAPA0 plus 1 minus XAPB0. So P total will become PB0 plus PA0 minus PB0 times XA. So this will be the expression of total pressure over a solution of over an ideal binary solution. Correct? And one more thing, we are saying in vapor form also both A and B are present. What will be mole fraction in this gaseous mixture? In vapor form, will the mole fraction of A and B will be same as that of in liquid solution? No. Because from the liquid solution, the component which is more volatile, that will evaporate more, and therefore in vapor form, the component which is more volatile will tend to have more mole fraction, will tend to have a higher mole fraction. Correct? So let's say in vapor form, mole fraction of A and B are given as YA and YB. Clear? So how can we find YA and YB? YA and YB are mole fraction in vapor form. So let's write terms each term. What is XA? XA is mole fraction of A in liquid solution. XB, mole fraction of B in liquid solution. YA, mole fraction of A in vapor. And similarly, YB, mole fraction of B in vapor. Okay. So how can we find our expression for YA and YB? So for YA and YB, we can apply Dalton's law for a mixture of gases. So what does Dalton's law says? Dalton's law says that partial pressure of gas in a mixture of gases is equal to its partial pressure by total pressure. So what will be YA? YA we can write as partial pressure of A by total pressure. That will be XA naught upon XA naught plus XB naught. And similarly, YB we can write as partial pressure of B by total pressure. That will be XB naught upon XA naught plus XB. So these will be the various relations in this section which we need to remember. What is partial pressure of A? What is partial pressure of B? What will be mole fraction of A in vapor phase? And what will be mole fraction of B in vapor phase? Okay. So let's see how we will apply it in problems. Directly, let's start with various problems of PYQ. So let's take this example first. There are two liquids A and B, and vapor pressure of pure liquids A and B are 400 and 600 torr respectively. On mixing these liquids, the sum of initial volume of liquids is equal to final volume of solution. Okay. So we mix these two liquids. The final volume is equal to initial total volume. Mole fraction of A in solution is 0.5. Find total pressure of this solution and composition of vapors above this solution. So see, in all such problems, we have to just analyze what is the initial data given, what we need to find, and apply the relevant expression or relevant formula. Okay. So here, what we are given, we are given PA naught. PA naught is given 400 torque. We are given PV naught 600 torque. This is given. We are given volume of solution is equal to VA plus VB. So that implies this is a ideal solution because delta V is 0. Okay. And next thing we are given XA as 0.5. Liquid solution में mole fraction is given 0.5. It means XA is 0.5. So we can calculate XB also. XB will be 1 minus XA. That is also 0.5. This much data is given. Once we realize this much is given, now we have to just apply the relevant equations. First, they are asking total pressure. Total pressure is given as XA PA naught plus XB PB naught 0.5 into 400 plus 0.5 into 600. So that will become 500 torque. Then they are asking composition of vapor phase, which is nothing but YA and YB. So how will YA and YB be given? XA PA naught by P total. So 0.5 into 400 by 500. So that will be 2 by 5. XB PB naught by P total. 0.5 into 600 by 500. That is 3 by 5. 0.4, 0.6. Where you can see as what I was saying previously. Liquid phase mole fractions were 0.5, 0.5. But in vapor phase mole fractions are 0.4 and 0.6. Mole fraction of B has increased and it should increase because B is the more volatile liquid. Vapor pressure of pure B is 600 while vapor pressure of pure A is only 400. So since B is the more volatile liquid, therefore vapor pressure mole fraction of B has increased. Okay. So quickly go through this before we move to next problem. Next example. Give this problem a thought. Very similar to previous problem. This is also a PYQ. Just quickly give it a thought. Okay. So let's see here again. Where again PA naught is given to us 7,000 Pascal. PB naught is given 12,000 Pascal. XA is given 40 mole percent, means mole fraction 0.4. And therefore XB 1 minus XA is 0.6. This information is given. And problem has already told us that this solution is a ideal solution. Correct? So now we have to find composition of vapor. We have to find nothing but YA and YB. So YA will become XA PA naught 0.4 into 7,000 by 0.4 into 7,000 plus 0.6 into 12,000. Correct? How much will this become? 1,000 cancels out throughout the equation. So 0.4 into 7, 2.8 by 2.8 plus 0.6 into 12 will be 7 point. So YA comes to 0.2. So YB, we can calculate 1 minus YA. That will be 0.7. Okay. Very similar problem to the previous one. Correct? Calculation of YA and YB. Next, इसी में let's take a slight variation. So this is the question now. We are given weights of two liquids mixed. Their pure pressure is given. And we have to find mole fraction of any one of them in vapor form. So let's call this as A and this as B. So let's first find moles of each. What will be molar mass of CH2Cl2? 14 plus 71. That is 85. So moles of CH2Cl2, 8.5 by 85. That is 0.1. Correct? And similarly, what will be molecular weight of CHCl3? 119.5. So moles of CHCl3, 11.95 by 119.5, 0. So basically we are mixing 0.1 moles of each. So mole fraction of CH2Cl2 as well as mole fraction of CHCl3 in liquid phase will be 0.5 each because equal moles are being mixed. Now we have to find Y of CHCl3. In vapor form, what is mole fraction of CHCl3? Mole fraction in liquid form 0.5 into pressure of pure CHCl3 200 by 0.5 into 200 plus 0.5 into 415. Correct? So how much will this become? 100. Yeah, you can cancel 0.5 throughout the equation. So 200 by 615. Correct? And this now we can simplify. 1 by 3 से काफी close है ये. Correct? चलो. Now let's take some integer type. Next problem, let's take so a gaseous mixture of two substances A and B. Gaseous mixture of two substances A and B under total pressure of 0.8 atm is in equilibrium with an ideal liquid solution. Is in equilibrium with ideal liquid solution of A and B. Okay. You are given if mole fraction of A in vapor form is 0.2. If mole fraction of A, mole fraction of A is 0.5 in vapor phase and 0.2 in liquid phase, then find pressure of pure A. Where some data has changed now. Similar problem, but data has changed. Now what is given? We are given mole fraction of one substance in liquid phase and vapor phase. Correct? And we have to find PA naught. Let's start. So here XA is given 0.2, YA is given 0.5. The mole fraction of A in gaseous and vapor forms are given to us. Clear? And P total is given to us as 0.880. So let's apply all things in various equations. So the first equation I can write that P total is XA naught plus XB naught. P total is given 0.8. XA is 0.2 PA naught. Then XB will be 0.8 PB. So if we divide the entire equation by 0.2, so we will get 4 is equal to PA naught plus 4 PB. This is one equation we get. Next, we can write the equation for YA. YA will be given as XA PA naught by P total. So YA is given to us as 0.5. That will be equal to XA is given to us as 0.2. PA naught we want to calculate. And P total is given to us as 0.8. So from here we get PA naught is equal to 2. Yes, you substitute in above equation, you also get PB naught. But anyway, that is not needed. We only wanted to find PA naught that we can get only by second equation. Okay? So go through this quickly. So try to see this problem. You can see these similar type of problems are coming again and again. We have to be just quick in such problems. Again, mole fraction of A is given in liquid solution. PA naught and PV naught is given. So PA naught 50 torr, PV naught 100 torr. XA 0.3. And we are asked YB. So YB will be equal to XB PV naught upon XA PA naught plus XB PV naught. If XA is 0.3, then XB will be 0.7. So substituting 0.7 into 100 by 0.3 into 50 plus 0.7 into 100. So that becomes 70 upon 15 plus 7. So this YB was given to us as X by 17 is 70 by 85 or 14 by 70. So that gives us the value of X as 14. Okay. Sure. So I think these type of problems are clear. Now, the next thing what we can do in these ideal solutions, we generally discuss regarding if we make a graph, we try to make a graph of P total versus XA graph. Now XA will definitely go from 0 to 1. Okay. So this graph is going to be in this range. How will this graph be for ideal solution? So the equation here we had was P total is XA PA naught plus XB PB naught, which we rearranged and write as PB naught plus PA naught minus PB naught XA. So if we see, this is equation of what straight line of format y is equal to mx plus c. So this graph will be a straight line of positive or negative slope depending whether PA naught is greater or PB naught is greater. So this is intercept will be PA naught when pure A, and this is pure B, so pressure will be PB. Correct? So for our ideal solution, P total versus XA graph will be a straight line. Okay. And similarly, if I plot P total versus YA graph, so this was XA. If I plot a P total versus YA graph, YA limits will also go from 0 to 1. So I can plot it in this same graph. So what was the expression here with us? YA is equal to XA PA naught by P total, correct? Which I can rearrange and write as PA naught by P total into XA. From above equation, I can write XA as P total minus PB naught upon PA naught minus PB naught, correct? So this I can rearrange PA naught minus PB naught upon PA naught. This I bring on left side into YA is 1 minus PB naught by P total. Correct? So now we can rearrange this. Let's bring this entire term other side. So what we will get? PB naught by P total is equal to 1 minus PA naught minus PB naught by PA naught into 1. You can take a reciprocal, correct? And we can see this graph is giving me a hyperbolic relation. So P total versus YA graph will be like this. Okay. Now, so this is a graphical representation of an ideal binary solution. And here, the region above yellow line is a pure liquid region. Means if we mix A and B in such conditions that we are above yellow line, then that solution will exist purely as liquid. There will be no vapors there. Similarly, the region below the pink curve is pure vapor region. Means if we mix A and B and keep conditions such that we are below pink line, then we have pure vapors. And the region between this yellow and pink line, here if we mix, we will get vapor liquid equilibrium. Okay? Means it will exist both as liquid and vapors will coexist in equilibrium. So let's elaborate this a little bit more in this graph and in a numerical. So let's take such a problem. And let's say there are two liquids A and B for ideal solution. Okay. This information is given to us. PA naught is, let's say, 600 torr. PB naught is, let's say, 300. Four moles liquid A is mixed with 6 moles liquid B to form an ideal solution. So this much data is given to us. Now based on this data, we are asked several questions. Let's see. First, let's say, first thing asked to us. What is total pressure of this solution? How we will calculate this? We will directly apply the P total expression, which is P total is XA PA naught plus XB PB naught. XA and XB you can see are 0.4 and 0.6 respectively. So 0.4 into 600 plus 0.6 into 300. So this becomes 240 plus 180. 4205. Okay. So this is the total pressure this solution can enter. Now, next part has to work in the problem. If external pressure over this solution is kept at 760 torr, how will this solution exist? This is what I was talking in this graph. Now, how much pressure this solution can exert? Only 420 torr. But how much external pressure we are keeping now? We are keeping external pressure 760 torr. Means if we analyze from the graph again, what we are talking here. This was our yellow line. This is pressure of pure A, 600. This is pressure of pure B, 300. We made a solution in which mole fraction of A was 0.4. So let's say this is 0.4 XA. Corresponding to this, what will be total pressure? Corresponding to this, the total pressure we were getting corresponding to this total pressure we were getting 420 torr. But what we have done? We have kept external pressure at 760. This was the liquid solution. By means of an external piston, we have compressed it, we have kept external pressure 760. Now, vapors of this liquid can apply a maximum pressure of 420. And from the piston above, we are pushing by a pressure of 760. So somehow this pressure has to balance. Vapors of this liquid cannot balance this pressure. So now this pressure can only be balanced by normal applied by liquid surface. So the piston has to be in contact of liquid surface. So in this graph, where are we? We are currently somewhere here, corresponding to a 760 pressure. And what I said, if we are above yellow line, then what will happen? Above yellow line, if we are, then the system will exist as pure liquids. There will be no vapors. No vapors, no vapor liquid equilibrium. You are keeping external pressure at 760. The entire solution will exist as pure liquid. Okay. Now, further, let's say we extend this problem further. And next part we say, now if external pressure is reduced gradually, at what pressure will first bubble of vapor appear and what will be its composition? Yeah. So now the problem is asking us that suppose we start decreasing this external pressure. So as we decrease this external pressure, means we are saying we start coming down this line. So now the problem is asking, at what pressure will I see first bubble of vapor? When will first bubble of vapor appear? First bubble of vapor means vapor and liquid are in equilibrium. And when will vapor and liquid be in equilibrium? When liquid can exert its pressure. And how much is the pressure exerted by liquid? 420. So first bubble of vapor, when we come down here, coming down, when we reach this point, here it can exist in equilibrium with its vapor. Okay? So first bubble of vapor will appear when we bring down external pressure to 420 torr. Correct? So our answer here will become, when will first bubble of vapor appear? When external pressure becomes equal to total pressure of solution, that is 420 torr. And at this, they are asking us composition of this vapor. So basically they are asking us YA and YB. YA we can calculate. XA was 0.4 into 600 by 420. So that will become 240 by 420 or 12 by 20. So the first bubble of vapor which will appear in that, mole fraction of A will be 12 by 21 and mole fraction of B therefore will become 9 by 21. Or simplify if you want, you can simplify it to 4 by 7. So 4/7 and 3/7. Correct? Okay. And one further thing in this we can add. Let's say next part. Let's thought in this problem say that if we keep on reducing external pressure, what will happen? If we keep on reducing external pressure, to balance that, pressure of solution will also have to change. It always has to be equal to external pressure. So more and more liquid will be evaporated, correct? And that will cause a change in mole fraction in liquid as well as vapor. And as more and more liquid will be evaporated, moles in liquid will keep on decreasing. Now this part is asking us that if we keep on reducing external pressure in this way, at what value of external pressure will the last drop of liquid appear? Means almost all liquid has evaporated. Only one small drop of liquid is left. This situation will occur at what external pressure? Okay. And also you have to find that what will be composition of that last drop of liquid. Okay. So now in this graph, if we try to analyze, this was our first drop of first bubble of vapor wali situation. If I keep on going down further, first I came from here to here. This was our first bubble of vapor. If I keep on going down further, I will somewhere reach here. And if I go below this is pure vapor region. So this is the point where last liquid vapor equilibrium can exist. And here you can see the x coordinate of pin graph is 0.4. Means mole fraction of A in vapor form is 0.4. And that should be logically clear to you. See, at last drop of liquid means almost all liquid has evaporated. If all liquid has evaporated, then these starting moles which we took, 4 moles of liquid A and 6 moles of liquid B, all of them have evaporated and gone into vapor form. If all of them have evaporated and gone in vapor form, then now in vapors there will be 4 moles of A and 6 moles of B. So now in vapor form, mole fraction of A will be 0.4 and mole fraction of B will be 0.6. That is what we are seeing in this graph here at this point. In the above point, yellow graph had a x coordinate of 0.4. Means yellow graph was for XA. It means at the first, this region, XA was 0.4. Mole fraction of A in liquid phase was 0.4. Here the x coordinate of pin graph is 0.4. Means YA is 0.4. Mole fraction of A in vapor form is 0.4. Correct? So last drop of liquid, what is our guiding condition? Here Ya will become 0 point. Yeah. So we have to find when will Ya become 0.4. What should be the external pressure there? And what will be the composition of that last drop of liquid? So let's see. Let's write expression for Ya. Ya will be XA naught upon XA naught plus XB naught. Ya is given to us as 0.4. XA we do not know now. Can't use XA 0.4 now. As liquid will keep on evaporating, mole fraction in liquid will change because A and B will not evaporate in the same ratio. So mole fraction in liquid phase will continuously keep on changing. So XA PA naught was given 600 upon 600 XA. XB I will write 1 minus XA and PB naught was 300. So 0.4, that is 2 by 5 is 6XA upon 6XA plus 3 minus 3XA. Correct? So what does this equation becomes? 2 by 5 is 3XA upon 6XA. 6XA upon 6XA plus 3 minus 3XA. So 2 by 5 is 6XA upon 3 plus 3XA. 3 से divide कर दो और 2XA upon 1 plus XA. So 2 plus 2XA is 10XA. So XA you get 2 by 8. That is 1 by 4. So one part of the answer becomes that composition of last drop of liquid. In last drop of liquid, mole fraction of A is 1 by 4. Okay. And next thing we were asked, what is the total external pressure? So external pressure has to be balanced by total pressure of solution. Total pressure XA PA naught plus XB PB naught. So 1 by 4 into 600, 3 by 4 into 300. So that will become 900 plus 600. 1500 by 4. 375 torque. Okay. So here again what we can analyze. The graph. So this pressure will be 375 torque. Okay. So in this mixture, when I mix 4 mole of A and 6 moles of B, if I keep external pressure above 420, then the entire mixture will exist as pure liquid. If I keep external pressure below 375, then entire thing will exist pure vapor. If I keep external pressure at 420, then almost entire mixture will exist as liquid and one bubble of vapor we will see. If we keep external pressure 375, then entire thing will exist almost as vapor. Just one last drop of liquid will be there. Correct? And if we keep pressure between 375 and 420, then both liquid and vapor will exist substantially. That also, let's take one example. Let's take one number 400. Let's see at 400 torr, how much liquid, how much vapor, and what are mole fractions. Let's also solve that. So let's say last part of the problem I take like this. If external pressure is 400 torr, then find XA, YA, and moles of A in liquid. So let's see. P external is 400. So it means total pressure of solution has to be 400. So I write equation 400 is equal to XA PA naught plus 1 minus XA PV naught. So we get 4 is equal to 6 XA plus 3 minus 3 XA. So we get 1 is equal to 3 XA. XA we get 1 by 3. YA we will get 1 by 3 into 600 by total pressure 400. So YA will be half. So at 400 torr, XA will be 1 by 3 and YA will be half. And then I also have to find how many moles of A are in liquid, total moles. Initially there were 4 moles in liquid A. So let's say moles of A liquid I assume in liquid form is N. Correct? And N1 let's say. And moles of P in liquid form, let's say I assume is N2. Mole fraction of A is 1 by 3 in liquid form. So I can say N1 upon N1 plus N2 is 1 by 3. That is 3 N1 is N1 plus N2 or N2 is 2N. Now if moles of A liquid are N1, total moles of A were 4. So moles of A in vapor form will be 4 minus N1. Agreed? And moles of B in vapor form, total moles of B were 6, will be 6 minus N2. In vapor form, mole fraction of A is half. Means A and B have equal moles in vapor form. So 4 minus N1 should be 6 minus N2. And N2 I write 2N1. So 6 minus 2N1. So we get N1 is equal to 6 minus 4, that is 2. So moles of A in liquid, 2. Moles of A in gases, 2. Moles of B in liquid, 4. Moles of B in gases, 2. So is this clear? Good day everybody. Bye everybody.